Welcome to part 5 in this series of 6 videos on division by zero. In this video, we will represent hypercomplex numbers with polar coordinates in a three-dimensional space. We'll extend Euler's formula, determine the norm of hypercomplex numbers, and define homotopic zeros. Let's begin with the representation of hypercomplex numbers using polar coordinates. In a Cartesian coordinate system, we represented a hypercomplex number h of the form a plus bi plus cz by measuring the real part a along the real axis, the imaginary part b along the imaginary axis, and the zero part c along the zero axis. When we want to represent h using polar coordinates, we set a equal to r times sine theta times cosine phi, where r is the length of the vector starting at the origin and ending at h. Theta is the angle that this vector makes with the zero axis, and phi is the angle that the projection of the vector onto the complex plane makes with the real axis. You can verify this in the illustration. In the same way, b is equal to r times sine theta times sine phi, and c is equal to r times cosine phi. So if we substitute those three in the representation of h, we get h equal to r times sine theta times cosine phi plus I sine theta times sine phi plus z times cosine phi. Okay, with this formulation, we can now extend Euler's formula. Euler's formula in 2 dimensions states that cosine phi plus sine phi equals the exponential of I times phi. This formula is quite handy in complex number calculation, but let's extend it to 3-dimensional hypercomplex numbers. In the expression for h, we can observe that the first 2 terms contain sine theta, indicated in red here. We can factor this out, and we obtain r times within brackets sine theta times within brackets cosine phi plus I sine phi plus z times cosine theta. Here we recognize, indicated in green, cosine phi plus I sine phi. According to Euler's formula, this equals the exponential of I phi. So we can rewrite the expression as h is r times between brackets sine theta times the exponential of I phi plus z cosine theta. And this is the extended version of Euler's formula for hypercomplex numbers. Let's now determine the norm of a hypercomplex number. For any hypercomplex number h of the form a plus bi plus cz, the norm of h, indicated by placing h between double vertical lines, is defined as the square root of the sum of the squares of a, b, and c. This corresponds to the length of the vector starting at the origin and ending at point h in the hypercomplex space. While we cannot visually represent 4-dimensional metacomplex numbers, we can still define the norm of a metacomplex number a plus bi plus cz plus diz as a square root of the sum of the squares of a, b, c, and d. This corresponds to the length of the vector from the origin to M in 4-dimensional metacomplex space. Finally, let's define the concept of homotopic or homotope zeros. In the hypercomplex space, when we've chosen a Cartesian coordinate system, the origin is a point with coordinates 0, 0, 0. This means that the real imaginary and zero parts of the origin are 0. However, all these zeros are distinct. Real 0 is not equal to 0i or 0z, and by extension to metacomplex number, it is also not equal to 0iz. Although the zeros occupy the same location in the hypercomplex or metacomplex space, they are all different from each other. The real 0 is the 0 that is obtained by approaching the origin along the real axis. This is the limit of the real part as it approaches 0. Similarly, 0i is the limit for the imaginary part along the imaginary axis, 0z for the 0 part along the 0 axis, and 0iz for the meta part along the meta axis. Because these distinct zeros are located at the same point in space, I refer to them as homotope or homotopic zeros. And that's all for now. In the description of the video, you can find a link to the article I wrote on division by zero. Please leave your remarks in the comment section below. Thank you for watching.